Okay, I'll make a start. Welcome, everybody. My name is Paul Goosens. I'm joined by Barani Mohan, who's our MBSE product manager, to talk about some of the new developments that we've been working on in terms of connecting some of our products together, and in the context of some of the projects that we're working on with some of our customers. I'm also here with Rochelle, who will, if you have any technical issues during the webinar, please feel free to chat with her. I expect that this will be about a 30-minute presentation, and with a live demo, just to show some of the work that we've done on this. And then hopefully we will wrap up for some questions after that half-hour session. So just to get started on this, thought I'd just start with a bit of an introduction to Maplesoft as a company in terms of its tools and also its expertise, because this is actually core to this presentation, that Maplesoft is more than just a product development company. It actually does have a significant number of engineers, software engineers, systems engineers that can help our customers to be successful with our tools. And certainly, that's kind of at the core of our engineering solutions capabilities. So really, it's this discussion is going to be much more about how our technologies and our expertise can be used to get value from calculations or managing calculations and analyses within your own organizations. Really, what we're talking about here is helping our customers to be successful in their digital transformation of their engineering processes through the use of our tools and our technologies, and of course our expertise. Because we'll be touching on we'll be touching on Maple and Mapleflow in this particular presentation. I just want to spend a little bit of time just talking about what Maple is, and also talk about Mapleflow, because that's a relatively new product for us. Maple, it's our core technology. It's a powerful symbolic engine married up to a user interface that allows our engineers to turn our users to turn mathematical concepts into solutions through the symbolic processing and manipulations of those expressions to get them into a form that can then be executed by plugging numbers in. But the critical thing here is that you can actually capture the knowledge behind that solution all the way back to the initial principles, the initial relationships. So that's an important key sort of factor of our tools, and it's actually one of the things I'll be talking about a lot in this session. But it's much more than just mathematical manipulation tool. Maple itself is a language. It's a programming language. It can be used to develop algorithms and routines that that are very powerful. You can combine that with why is this not working? Okay. You can combine that with user interface components in order to build deployable solutions that don't require the end user to know anything about Maple. So really, we're providing an environment where you can go from basic principles right the way through to a canned solution that could be deployed either with Maple or through our web publication tools, Maple Cloud. And they're probably one of the best kept secrets of Maple is that you can actually generate code from those solutions. So a lot of our customers are taking these solutions, generating C or Java or Python and even Fortran to embed those solutions in their own tools. So very powerful and really a lot of value there for our customers. Mapleflow is kind of the other extreme. It assumes that the equations, the expressions are already derived, and it provides a sort of calculation document tool that allows you to place your expressions wherever you want it on the page, and build up what are effectively live technical documents. Calculation documents, largely targeting our design engineers and scientists, who really all they want to do is to take already existing equations and implement them in an environment that looks like a live, like a design document. I won't dwell too much on the details here, but the idea is that you can combine mathematics with text and graphics, and of course it still uses it's using our very powerful dimensional analysis, dimensional units capability to keep track of units throughout the calculations. Again, that's a very important factor for our technologies. And actually, really, under the hood, you can still the Maple kernel is still there, so you can actually access a lot of the Maple power from within the Mapleflow document. So that's just to give you a bit of an introduction to what these tools look like. Being used by many customers, many engineers, scientists throughout the world. For many larger organizations, I particularly tend to get involved in some of the bigger companies that are very complex, that is designing complex products, and of course they are now trying to understand what it means to integrate many of these processes together in order to achieve some of the digital transformation initiatives that they see as going forward in their business. And the big challenge there is really that these organizations tend to start getting very siloed, and there are many different tools, different approaches. It's largely uncontrolled. Most of the knowledge resides with the subject matter experts, and that can be easily lost if that SME leaves the organization for whatever reason. The design decisions they can be they can be captured in many respects, and typically in systems models, but the actual steps to getting to that decision are sometimes lost. And so the challenge is, how do you maintain a consistent approach to managing engineering calculations that satisfies the needs of all the stakeholders, because everybody will have different interests and information gets siloed for a reason. Is there a way that this can be managed that benefits all stakeholders? And this is where we are coming from. Certainly in the context of design calculations, which is the sort of expertise that we built our capabilities on. We get exposed to information that's coming from many different parts of the organization that need to be brought into the design calculation. So these could be requirements coming from a systems engineering tool. They could be simulation analysis management coming from, say, from a PLM system. It could be design parameters that have been captured in a product data management tool. It could even be external information that's coming in from elsewhere in the supply chain. All of this information has to be brought in and effectively tracked in order to create those calculations. And then, of course, once the results have been generated, how do you manage those results, and where do what generated those results? What were the circumstances for doing that? And then any design decisions have to be captured in that way as well. So under the hood in our Maple technology, we have amassed a quite considerable wealth of capabilities that allow for tighter integration with other tools within your organization, whether it's file-based or databases, whether they are dedicated simulation languages, whether it's just code. We can handle all of that. The one I'm going to actually talk about more today is in terms of our online connectivity. So our TCP/IP backend, our recently launched Open API that allows us to configure the API for any REST-based web service is critically important to a lot of the activities that we're involved in. So, but that's what actually it means is that now we have a way of being able to connect all this information, all this capability into this, into the broader organization through, what's often described as the digital thread. But the critical thing here is that the knowledge that went into developing all of this is now encapsulated in a way that can be actually deployed and reused within the organization. And that's the goal of what we're trying to do here. How do we do it? Well, we have this thing called Maple. Maple's kernel. We use it in our own tools as the sort of the engine, the mathematical engine. Obviously, Maple and Flow, and also Maple Sim. But we can use it for third-party tools as well. So we have the ability to integrate, for example, with Python, but also with MathWorks tools and so forth. And then what we want to talk about today is how can we tie in that capability into systems models, into the architectural models that are created using languages like SysML and Capella. And the reason we see this as Maple can bring value into this particular domain is that we can handle equations. We can actually not just equations, expressions. We can combine them. We can simplify them. We can causalize them, so you can determine what are the unknowns, what are the knowns, much later in the process. We can handle constraints, inequalities. We can actually do consistency checking, so we can see if there's missing data, or if there's inconsistent data that's going to cause not only an error in the calculations, but should be flagged as an error in the design. And we offer a wide range of analytical capabilities. I'll be talking a lot about our units handling, because I think it is actually critically important that we can do this. And it's not just basic conversions. We are handling engineering units at the dimensional level. That means it's much easier for us to do conversions, but it's also really useful for error trapping. It's quite amazing just how many calculations actually deliver inconsistent dimensional units. So we use that a lot. But you can go beyond that, differential equation systems solving, graph theoretic approaches for analyzing networks and optimizing structures. And and more recently, we're starting to see an increasing interest in machine learning. And we have a fair bit of capability already in Maple for doing this kind of work. And then we are able to then deploy those solutions. We can take those results, or those executables, and turn them into something that can be used beyond the tool chain, whether it's in the web. It's generating FMI capable code blocks, S functions for Simulink, and so forth. So these are really important capabilities, that we can see can bring a lot of value to the to implementing calculations for systems models. Okay, so this brings me to really the topic of of today's discussion, and that is we have recently I'll describe it as a soft launch launched the Maple connector for SysML. So this is an add-on library to Maple that allows us to interface the Maple engine to parametric information within the systems model. At present, we support Teamwork Cloud. We are exploring other MBSE platforms, and this really, this is the purpose of this presentation, is to start generating interest in how this tool could be used and what other platforms we should be considering. As many of you probably have heard, that there is a new implementation of SysML coming out, I'll say early 2024. We're looking very closely at that. There are some aspects of that which I'll talk about later in this presentation that actually makes it a much, a very natural fit for the kind of work that we're doing. And just to close off this whole discussion of integrating with systems models, I do want to just talk about the work that we're doing with Zook and Vitek. So we have been working on an integration with their Genesis systems engineering tool. We completed that early in the summer, and it's now being presented. It'll be presented at the Zook and Integration World Conference in Japan next week. So Genesis isn't based on SysML. It's using another proprietary structured language, but the critical thing here, it's still a structured model that we can decode and turn into something executable. So what do we mean by this? So fundamentally, what we're doing with the systems model is that we can access the structured data from within the source of truth, the architectural model. Typically, this will be found in the sort of parametric sections of the model. But the important thing here is that we can grab that structured data and then extract out any explicit expressions, any implied expressions, just in terms of what the structure of the model is telling us about the mathematical relationships that are in there. So there are some inherent mathematical relationships that we can derive from that. We can grab the parametric values and their engineering units, and we can take this a step further. We can actually generate code from that. From those expressions. But the important thing here is that we can turn these into what I would describe as executable assets. So now we're taking knowledge or information that's residing in the system model and turning them into something that we can actually perform some calculations with and make some design decisions from it, whether it's equations going into the Maple flow environment or expressions that are going into the advanced mathematical analysis of Maple. Indeed, we can even extend this to generate Modelica models. We don't have that just yet, but it's definitely a possibility. And of course, we can take executable code, and that can be integrated into any tools beyond our own. So the idea here is that these tools can be used to, these assets can be extracted from the system model, some kind of analysis performed on them, and then conversely, we can take any results that come from those analyses and push those back into the system model, if it makes sense to do that. But now, really, we have this, certainly in the context of systems models. We have a very, very solid way of being able to integrate engineering data into the digital thread. And I think for now, I will pause my presentation there and just show you what this thing looks like.
In this demonstration, we're going to be working with this system model of a multi-stage jet engine. This is how it appears in Cameo Systems Modeler, and it resides on the Teamwork Cloud server. It contains the system design in terms of requirements, structure, behaviors, and design parameters. These parameters are in the respective subsystems, and we're going to use these to perform an analysis in Maple. In order to do that, we'll need to know the location of each parameter from the systems engineer in charge of the model. The locations are found by inspecting the value properties for each parameter and locating the qualified name. This is effectively a path to the parameter, and each path can be copied and sent to the engineer during the analysis. Now let's go to Maple. Here we have a calculation worksheet that's been developed to perform a thermodynamic analysis of the gas flow to determine the specific fuel consumption. First, we need to connect to Teamwork Cloud using Maple's SysML connector. We log in with our credentials, and then we can use the qualified name paths from the systems engineer to start extracting the parameters we need from the system model. Notice that not only is Maple acquiring the numeric values, it's getting their engineering units, so we can use Maple's dimensional analysis capability to support the use of units throughout the calculation. We can use it to convert to different units if we wish, but the important thing is that Maple maintains the dimensional integrity throughout, not just for unit conversion, but also for spotting errors and fixing them. Once we have all the parameters from the system model, we can start the analysis. In this example, we're determining the mass and energy flow at each stage in the engine, and we'll be using Maple's thermal properties library to help us. Given the internal energy and air fuel mass flow at each stage, we can calculate the amount of fuel required to maintain the aircraft speed and altitude. From this, we can calculate the specific fuel consumption, or the amount of fuel required to deliver a kilonewton of thrust. This is our measure of performance that we can use to make sure the engine complies with the design requirements. To finish off, it's useful to visualize the energy states at each stage in the cycle on a temperature entropy chart. Now we have a design sheet that's fully integrated with the system model. If any changes are made to the system design, we can quickly recompute the SFC and flag any issues that might arise from these changes.
So this is this is one use case that we've been playing around with. So can we create design worksheets that take parameters from the system model? And indeed, this is what we've done here. Well, we can take this a step further and actually extract any equations, any expressions that reside in the system model. We can then use these to combine together, and then perform some kind of execute some kind of calculation. So there's a lot of heavy code in this, but it's just really to give you a sense of the what can be achieved with all of this. And then at the very end, we have the results that we're looking for. So we can that we can automate this whole execution without really having a design document. Just have this as a way of executing the calculations over and over again. By the way, there's a much more extensive demo video which I can point to you at the end of this session. So that's really what we're proposing and what we're working on, and really the idea is to get people thinking about how we can use our technologies to extract structured information and turn that into something that can be turned into calculations. And one of the reasons that's driven us to this is actually the activity around SysML2. I'm just going to go back to my presentation. One of the extensions to SysML2 is the ability to capture analysis semantics. I'm not going to go into the details in this, but this is actually just an extraction from the definition, from the standards definition, and the goal really is that anything that pertains to a calculation for some kind of measure of performance can be encapsulated in the system model in terms of and defined in terms of what the analysis objective is, what kind of model you're going to be using, and how those properties are going to be handled or managed within the SysML2 model. We think this is an exciting development, and we've been part of the SysML2 definition team in order to make sure that we understand what is required for doing this, for when customers start to use SysML2 within their own tools, which is largely going to be determined by when the vendors make SysML2 available. But the idea is that we're already experimenting with this. We've already built some prototypes and presented them, and generated a lot of interest in that. Okay. That was my slide, just to say that we actually do have a connector prototype that we've been playing with, and again there are some demo videos that I can point you to on that. Okay, just to wrap this up, really, where can this go? I mean, from our perspective, there is we see that there's a need for this capability in the models. We're already experimenting with the Maple connector and with the SysML connector, and you've seen that certainly in the context of Vitek Genesis, that there seems to be a growing need for integrated analysis or analysis capabilities integrated into the architectural tooling as well. So this could be a very interesting area to be developing with other systems tool vendors. But from our perspective, I think what is going to be really exciting is the fact that customers can create their own libraries of formulas, of expressions, of computations, and tie them into the systems model and actually capture the semantics. What are these things going to be used for within the systems models? So there's potential here for internal design manuals to be implemented as systems models. From our perspective, we see potential for commercial libraries, standards libraries, and so forth, that could be could reside in the systems model and then implemented using our technologies. And I think we could even see this going a step further, in the sense that not only does Maple become a consumer of all this information, but also Maple could be used as a tool for authoring that information to reside into the systems models. So that we see that this is actually it could be a very exciting development in the systems engineering world. So that's really where we feel this can go in terms of next steps. Really, what we'd like to do is engage with some lead customers to understand how they could see technology like this being used. Why us? Well, we do have a lot of experience in this. We've done a lot of development work, either solution development work or software development work. We can provide everything from, you know, a bank of equations to a turnkey solution. And of course, you know, we see this as a way of being able to drive the return on investment. You know, really just in terms of where we can see this going with the connectivity between the systems model and our analysis tools, we can really help organizations to eliminate a lot of the churn, you know, unbudgeted costs, disruptions that typically are you know, that are sort of built into the process. We can smooth a lot of that out. We can help our customers in terms of getting that improving time to solution. And you know, I think there are just many different ways and many benefits that to bring value to the process. And, you know, and overall, you know, it just helps to maximize the return on your calculation and analysis tools. So with that, really, I'd like to thank you for your time and attention. We'll get on to questions in a moment. But fundamentally, this is kind of in terms of the next step. If anybody wants to try out the SysML Connect for themselves, we are providing it free of charge as long as you acquire a license of Maple 2023. We can, if you want to do that, we can talk about pricing through our sales organization. If you'd like to engage us in a pilot project to show how this technology could really bring value to your organization, come and talk to us. You can connect with us directly through info. Well, it's actually indirectly through info@maplesoft.com, or you just talk to me. You can contact me directly, pgoosens@maplesoft.com. And that's it. Thank you very much for your time and attention.